In this video, I want to introduce the topic of Newton's second law, or kinetics, which is basically the next branch of dynamics that we talk about. And the basic principle behind Newton's second law of motion is that the motion of an object is the result of a force or a net force acting on it. And whether that net force causes translation or rotation depends on the geometry of what we're talking about and the types of loads involved. So where this topic differs from what would be covered typically in like a statics course is that, of course, in statics, we stick pretty closely to Newton's first law, which more or less gives us that the summation of forces is going to be equal to 0. And the second law gives us that the summation of forces is no longer going to be equal strictly to 0. And in exchange, we end up with now the summation of forces being equal to the mass times the acceleration of that object as it undergoes motion. And of course, remembering that these are vector quantities, which means again that we can divide them up into Cartesian component directions, or I guess any other coordinate system that we might want to use. So we can have an fx, fy, and fz, and so forth, or any other coordinate system that we might have. So when it comes to actually solving problems, that can be pretty useful in that we might break those things up into the summation of forces in the x equals the mass times the acceleration in the x direction, and the same in the y, and the same in the z, of course, or again, any direction that we might want to talk about. If we are talking about objects that are undergoing a moment or a torque being applied to them, we need to think about rotation as well. So the rotational component that we include is a summation of moments, and instead of again setting that equal to 0 like we might in a statics class, we're going to set this equal to mass moment of inertia times angular acceleration. And again, these are also vector components, meaning that they have directionality associated with them, and we can rotate about different axes and break those up into those components. But the net result is that we have lots of different things to potentially consider, and it all kind of depends on how our forces are acting on the body. So for example, if I pick my kind of arbitrary block object that I use in many cases, now I'm going to label where the center of gravity of this block may be, pretending that that's directly in the middle. Now if all of my forces that I apply to this act through that center of gravity, so their line of action passes through that center of gravity, then I'm not going to be worrying about rotation so much. I'm only going to be worrying about the summation of forces and how this thing might be moving in space as a result, but not how it's rotating, right? And we're kind of treating this then as a particle. Now, that's kind of a distinction then, whether or not we're talking about a particle or we're talking about what we might call a rigid body. In a rigid body, we can have the same sort of shape with the same center of gravity location, but now suppose I have forces acting on different locations that don't necessarily have lines of action that are coincident with the center of gravity. Now these things can cause rotations of this object and produce some sort of rotational outcome in terms of angular velocity denoted with an alpha here. Similarly, I could apply a torque or a moment directly to my rigid body. So I could apply a force, let's call it a torque, T, to this. Say for example, I put a screwdriver into something and twist it. That's applying a direct torque to that object and causing rotation. And all of that comes into play in terms of how this rigid body might respond to motion. And that's what we'll be analyzing as we start to get into kinetics and working through the different mechanisms that we have for how to solve these types of problems. Thank you.